All right, we're going to show the connection between simple harmonic motion and circular motion. So you can see this apparatus right here. We have some lights up here, and there is a circular object here that's going around in a circular path. And that red dot there, the shadow of that red dot is being projected on this paper. And if you think about what the shadow would look like as this thing rotated around, it would oscillate back and forth with simple harmonic motion. At the areas of greatest amplitude, the velocity would be zero here and here, and as it went through the equilibrium position, its velocity would be maximum. Furthermore, if the paper was moving, then it would trace out a path here of a sine wave, or we sometimes call that a sinusoidal motion. And if you look at the graph down here, this is just taking this piece of paper and showing you horizontally that this would be the period from here to here, and that's 2 periods, 3 periods, and so on. And then this is the amplitude in the positive direction, amplitude in the negative direction, and right in the center would be that equilibrium position. This diagram over here shows the object as it moves around in circular motion. And then down here, this would be the projection of this object on the paper like we saw in the previous slide. Down here, that object would be moving at simple harmonic motion. Okay, so we can use this to derive a few equations. So the first one we want to look at is what was the displacement of the object. Okay, so right down here, I'm talking about the displacement of the object oscillating with simple harmonic motion. There it is, x, and then there's the angle theta, and then this is the radius of the circle, but the radius of the circle would be equal to the amplitude. So we can say that the cosine of theta, this is the right triangle, is equal to the adjacent x, the amplitude, the distance from the equilibrium position divided by capital X, which is the amplitude. And if we solve for x, we get x is equal to the amplitude times cosine theta. All right, now we had seen previously that the connection between angular velocity and angular displacement in time, you might recall that, hopefully you do, that angular velocity was equal to angular displacement divided by time. So if we solve for the angular displacement, it's equal to the angular velocity times time. And furthermore, the angular velocity was 2 pi f times time. So if we take that, substitute it in here for theta, what we end up with is x, the displacement, is equal to the amplitude times cosine 2 pi times the frequency times the particular time interval where you want to compute the displacement. Or if you want it in terms of period instead of frequency, you can use this equation. Okay, so let's move on to velocity. All right, up right here at this point, the velocity here, that's the maximum velocity. This object's velocity does not change when it goes around the circular path, and it's always just equal to the maximum velocity. But the velocity of the object moving with simple harmonic motion is this component of the velocity right here. So, again, we have a triangle. Notice that this angle theta and this angle theta would be the same angle. And if we use the sine function, the sine of that theta would be equal to the opposite side v divided by the maximum velocity. Or, solving for v, the velocity at any point is equal to the maximum velocity times sine of theta. If we do the same substitution that we did up here, that would mean that the velocity of the object is equal to the maximum velocity times sine of 2 pi ft, or same equation in terms of period. Okay, now, also from the circle, we can see that the period of this object moving around the circular path, which would be the same period as the object oscillating with simple harmonic motion, that's going to be equal to the total distance, which is the circumference of the circle, 2 pi r, or in this case x, because x is the radius of the circle, divided by V max. And we said before, in the previous video, that V max is equal to the square root of k over m times the amplitude. So if we substitute that in here, and the x's cancel, then we're left with t is equal to 2 pi times the square root of m over k, or in terms of frequency, f is equal to 1 over 2 pi times the square root of k over m. So you could use these formulas for a mass that was oscillating with simple harmonic motion on a spring, horizontally or vertically, and all you would need to know is the mass of the object that's oscillating, and k, which is the spring constant of the spring. Interesting, the period does not depend on the amplitude. So what that means is, if you've got this mass hanging on a spring, it doesn't matter how far you pull it down before you release it, the period and the frequency will be the same. All it depends on is the spring constant and the mass. Here's a problem that uses that previous formula. So we have a spider which has got a mass of 0.3 grams. He waits on a web of negligible mass. A slight movement causes the web to vibrate at a frequency of 15 hertz. We want to estimate the spring constant K for the web. So since we have the frequency here, we're going to use this form of the equation, and we want to solve for the spring constant. So we're going to have to square both sides of the equation and solve for k. So when we do that, we get k is equal to 4 pi squared f squared times m. So we have 4 pi squared. This is the frequency. Again, notice that its units are shown as 1 over seconds. Hertz is a cycle per second, but the cycle doesn't show up in the unit analysis. So it's really just 1 over seconds, or seconds to the minus 1. So we've got to square that, and then the mass of the spider, that's got to be in kilograms. So 0.3 grams is 3.0 times 10 to the negative 4 kilograms, and we work through the numbers, and it comes out to be 2.7 newtons per meter. Another example of simple harmonic motion is a simple pendulum. And all a pendulum is a mass that's tied on a spring, and you take the mass back and you just let it go and let it swing or oscillate back and forth. Now you can see from this diagram that the force that tends to try to bring it back to the equilibrium position is, it's called the restoring force, by the way, and is equal to mg sine theta. Now we can forget about the negative sign, it would be negative, but it's positive on this side. So it's mg sine theta. So k is equal to f divided by x, and if we substitute in for f, that's mg sine theta divided by x. Okay, now, but for small angles, the sine of theta is equal to theta in radians, or I should say approximately equal to. It's not exactly equal to it, but it's pretty close. And you might try this on your calculator. Try 3 degrees, the sine of 3 degrees, and compare that with 3 degrees converted to radians. You'll find that they're just about the same number. So that's what we're going to do. We're going to use theta here instead of sine of theta. But we know that theta definition of that. And if you look at this diagram over here, here's the angle theta. Here is this length of the arc here, S divided by L. Okay, so we're going to approximate and say that this S here and X are the same. And they are very close, especially when that angle is small. So, substituting that into here, we get mgx divided by lx, and you can see the x's cancel. And now, if you take that k and you substitute it into the formula that we derived in the last slide, right here, what we end up with is t is equal to 2 pi times the square root of L over G. So this gives us the period for a mass that is swinging back and forth with simple harmonic motion. And this is very interesting because the period only really depends upon the length of the string, and G, of course, but as long as you're on the surface of the Earth, G is always going to be the same. So it doesn't depend upon the mass here of this object, nor does it depend upon the amplitude of swing. So it only depends upon L. And the other interesting thing about this is it gives us a very convenient way of measuring the acceleration due to gravity. All you have to do is set up a pendulum, measure the period, measure the length of the string, and solve for G. Everything we've been discussing so far has been simple harmonic motion where it's oscillating, for example, on a frictionless surface. But of course, in the real world, there is always some kind of a force that removes mechanical energy from this oscillator. And that's what's called damping. Now, this diagram over here shows a small amount of damping, underdamping as it's called. And you can see that the frequency stays pretty much the same, but the amplitude just gradually gets less and less and less until eventually drops to zero. Now, if you increase the damping, in other words, you increase the rate at which energy is being removed, you come to a point that's called critical damping. And in critical damping, that allows the object to return to the equilibrium position most rapidly. And that's shown here in graph A here. So here is the displacement from the equilibrium position, that's x. Here's where you start, x0, and then this is time. So as you can see, the object goes back to the equilibrium position in the shortest amount of time. Now B, on the other hand, that's overdamping, and that's increasing the rate at which energy is removed at still a greater rate. And that takes the object longer time to return to the equilibrium position. Now, oftentimes things that oscillate have damping mechanisms that are purposely designed so that the object reaches its equilibrium position quickly. So a good example of this is a shock absorber in your car. So your shock absorber is a spring, and you go over a bump, and the springs oscillate up and down. And there are damping mechanisms in there, and the damping mechanisms is initially designed so that the amount of damping is the critical damping, so it stops oscillating, the springs stop oscillating at the shortest amount of time. But you might know this, that if your shock absorbers start wearing out, then what happens is the damping gets less. And when the damping gets less, you're now in a situation of being underdamped. And in underdamped, the oscillating continues for a much longer period of time. And that's how you tell if your shock absorbers are worn out. You just take your car and push down on the hood, for example, And if it just bounces up and down, up and down, up and down for a long period of time, you know that the shocks need to be replaced because the damping mechanism is not working as it's designed. The last thing that we want to talk about is something called resonance. Now, objects that oscillate have their own natural frequency. When you, for example, take a weight and you pull it down, it oscillates with its own frequency that depends upon the mass that's attached to the spring and the spring constant. So if you apply an external force on the system, that external force can have its own frequency. So in other words, you can apply a force on a system that's oscillating with simple harmonic motion with a force that's got a frequency of its own. Now, when the external force, the frequency of the external force matches the natural frequency of the vibrating object, you are now said to be at the resonant frequency. And what you'll observe is that the amplitude of vibration continue get bigger and bigger and bigger and reach the highest point at resonance. So here's a few examples of resonance. Used to be a commercial on TV that was for the Memorex tapes, and they had, I think it was Ella Fitzgerald, and they said that she could break glass with her voice. And that's possible because the way it would work is that her voice would have to match the natural frequency of it would be crystal glass, and that would cause the crystal to begin to oscillate back and forth with a high frequency that's being matched by the frequency of her voice and break the glass. Another example that's probably more familiar to you is pushing a child on a swing. So if you've ever done that, and I'm sure many of you have, if you match the frequency of the pushes with the frequency that the child is swinging, then the child goes higher and higher and higher. In other words, the amplitude of the swing gets greater and greater, and that's resonance. And of course, if you apply those forces at a frequency other than the same frequency, then it's not going to do much to increase the amplitude of the child swinging. Another great example is the Tacoma Narrows Bridge collapse. And I have a video of this. It's very interesting. It happened, I think, back in the 20s. And basically, it's just the wind velocities had a certain frequency that happened to match the frequency of the bridge and ultimately caused the bridge to come apart.